Greetings once again, Mr. Bailey here, talking you through the second lesson of Year 13 differentiation. So we've seen how to differentiate before trig functions, sines and cosines. Now we're going to have a look at how to differentiate exponentials and logs. But more than that, we're going to find out why these results work and prove them later on in this chapter. So these first couple of lessons are giving you the tools, and then you'll find out the understanding a bit later, if that makes sense. So before we start properly, let's have a few warm-up questions to get us in the mood. Here they are. So try them now, press pause, then press play when you're ready to see the solutions using this video. Okay, so assuming you've tried these now, let's have a look together at question number 1. So question 1 is a direct, basically a regurgitation / revision from the first subchapter on differentiation for year 13. So we did this last time, proving from first principles that the derivative of cos x is minus sin x. This is a crucial result. You need to know how to prove it very well indeed. So step by step, what I would suggest is we just start by saying let f of x equal cos x. Then by the definition of the derivative, f dashed of x will be the limit as h goes towards 0 as f of f plus x plus h minus f of x all over h. We can now use the compound angle formulae for cosine of x plus h to rewrite this in terms of cos of x plus h. First of all though, just substituting in what f is in terms of its cosine of x, we have this. Then like I say, using the compound angle formula, we can replace cosine x plus h with cos x cos h minus sin x sin h. Now if we see here, we can factorise out cos x and sin x. So if we factorise out a cosine of x, that leaves us with cos h minus 1 all over h, which is this useful limit here. And in pretty much the same way, we can factorise out a sin x. So if we factorise out a positive sin x, we'd get minus sin h all over h. So we can isolate this limit here. So the next step, factorising within this limit, we need to have this. And then we can use these given results to know that cos h minus 1 over h, that will shrink down to 0 in the absolute limit. So this will become 0 times cos x, and sin h over h will become exactly 1. So this thing here will become 0 multiplied by cos x minus 1 multiplied by sin x in the limit as h goes towards 0, because like I said earlier, and like we've been given here, cos h minus 1 over h will shrink down to 0, and likewise sin h over h will become exactly 1. So this becomes minus 1 multiplied by sin x, in other words, simply minus sin x, which is what we wanted to prove. So to conclude, if f of x is cosine of x, f prime of x is minus sin of x. Question 2, sketch the graphs of y equals e to the x and y equals ln x on the same axes, and also include and label any lines of symmetry. This is just a test of understanding. You need to remember and need to know that e to the power x and the natural log of x are inverses of each other. So the graph of y equals e to the x is something like this, characteristic curve where it goes up very, very steeply, literally exponentially, and it will cross the y-axis here at 1. Not that we need to label that because you didn't need to in the question. ln of x bends the other way, like so, and the characteristic curve of ln x is like so. And again, this will cross the x-axis when x is 1, because ln of 1 is 0. Then the line of symmetry will be the line y equals x, going between these two. So if we have two graphs where one is the inverse of the other, the line of symmetry between the two lines will always be the line y equals x. Question 3, we have f of x equals minus 3x cubed plus 8x squared minus 9x plus 10, where x is a real number. We need to calculate now f of 2. So f of 2 just means we're going to substitute in that x is 2. So we have minus 3 times 2 cubed plus 8 times 2 squared minus 9 times 2 plus 10. So let's just see what this gives us using, of course, the calculator. So all we're doing here, just to say again, is we're replacing x, we're substituting in for x for the value of 2. So if we try this now on our nice fancy calculators, minus 3 times 2 cubed plus 8 multiplied by 2 squared minus 9 times 2 plus 10. This is going to give us a result of 0. And we should know that if f of 2, if 2 is a root, then we can say therefore x minus 2 is a factor of f of x by the factor theorem. The question didn't ask us that, but we'll need it for part B. So for part B, write f of x as a product of two algebraic factors. Because f of 2 is 0, we now know we can divide this polynomial by x minus 2 with 0 remainder. So I'm going to show you the standard algebraic division way now. I'll show you the box method after, in case you prefer that way, which some of my class do, which is understandable. But doing it the textbook way, if you like, I'll just remind you how to do that now. So first of all, we divide the highest power in what we're dividing by the highest power of what we're dividing it by. So the highest power here is x cubed, so we're going to divide the minus 3x cubed by the x. Minus 3x cubed divided by x will give us minus 3x squared. Next, we multiply this by the highest power of x on the outside. That'll give us minus 3x cubed. Minus 3 times minus 2 gives us plus 6x squared. Now this next step, we now subtract. This will always cancel. 8x squared take away 6x squared, that gives us 2x squared. And then we always need to remember to bring down the next term along, which is minus 9x. Now we go again. Now we do 2x squared divided by x, which gives us just positive 2x's. Then multiply 2x by the x minus 2. 2x multiplied by x is 2x squared, and 2x multiplied by minus 2 gives minus 4x. Next step is to subtract. The 2x squared take away 2x squared cancels. Minus 9x minus 4x is minus 9x plus 4x, which takes us to minus 5x. Then, of course, we need to remember to bring down that positive 10. With no other numbers to bring down, so this is going to be our last step. That 10 is our last one to bring down. So finally, minus 5x divided by x gives minus 5. Then minus 5 multiplied by x, of course, is minus 5x. And minus 5 multiplied by minus 2 gives positive 10. And as expected, if we do this line, take away this line, we get 0 remainder, as we knew would happen. So therefore, we can conclude and say that, so f of x, which is minus 3x cubed plus 8x squared minus 9x plus 10, as a product of two algebraic factors, that's going to be x minus 2 multiplied by minus 3x squared plus 2x minus 5. So that's the textbook way of doing it, if you like. The box method, which I'm not going to go through in too much detail, looks like this. And so again, you write down the side what you're dividing by. On the inside, you need to aim this for what you're dividing. So I'm not going to go through the full method here, but if you try the grid method, that is something what it should look like on your end. So either the standard way or the grid method, you should arrive at minus 3x squared plus 2x minus 5 when f of x is divided by x minus 2. Finally, question 4, we're going to use what we did on question 3 to help us here. So for part A, prove that there are exactly two real solutions to this equation here. Now, before we jump into this, I'm just going to explain a bit from question 3 and build up the understanding. So first of all, from question 3, we had minus 3x cubed plus 8x squared minus 9x plus 10 equals 0 can be rearranged into this form here when we factorize it into two algebraic factors. So let's just look at these two factors and see where the solutions may lie. So first of all, are there any solutions from this factor here, minus 3x squared plus 2x minus 5? How many solutions a quadratic has is told to us by the value of the discriminant. So the discriminant, which we can use a triangle function here, delta, is b squared minus 4 multiplied by a multiplied by c. So a is a coefficient of x squared, b is a coefficient of x, c is a constant term. So our a, b and c here are minus 3, 2 and 5 respectively. So subbing in these values, the discriminant would be 2 squared minus 4 multiplied by minus 3 multiplied by minus 5. If you compute these values here, that becomes 4 subtract 60, which is minus 56, but importantly, the main thing is that's less than 0. And we need to recall, if the value of discriminant is less than 0, that means there are no real solutions from that quadratic. So from this quadratic here, there are no solutions. So any solutions to this cubic equation must come from this first factor, the x minus 2. So what solution would we have if x minus 2 needs to equal 0? This is obviously very obvious. This root here, as we proved from question 3, this root is x equals 2. So the only real solution is x equals 2 because this one here has a negative discriminant. So how does that help us for question 4? Because we're not talking about x cubed, we're talking about y to the power 6. But if you compare these powers here, all the powers of y are double the powers of x. So that's a clue that we can make a substitution that x equals y squared. So for part A, if we sub x equals y squared into the factorised form from question 3, this form here, we'd get this. So we start with x minus 2 minus 3x squared plus 2x minus 5 equals 0, and replace each instance of x with a y squared. So x becomes y squared, x squared is y squared squared again, which is y to the 4, and so on. So from what I mentioned before, because y squared is x, then y squared 2 will have no solutions from this one, because the discriminant here, like we mentioned before, is negative. So the only solution, or solutions for y, will be from this factor here. So the only real solutions are when y squared equals 2. Therefore, if you square root both sides and consider both positive and negative, y is either minus root 2 or positive root 2. So minus or plus root 2, that is, of course, just 2 solutions, either plus or minus root 2. Part B, we can now actually use, again from question 3, subbing in this time that this x is now tan theta to solve this trig equation. So for 4b, if we sub x is tan theta into this factorised form, we get this here. And in the same way as 4a, this minus 3 tan squared plus 2 tan theta minus 5 equals 0, which is a hidden quadratic, again will have no solutions for the same reason about the discriminant I mentioned before. So the only solution here will be where tan theta minus 2 equals 0. So in other words, if tan theta minus 2 is 0, the solution is tan theta equals 2. So if you do tan minus 1 of 2 to 3 decimal places, the principal value of theta is 1.107. We're not asked for the actual solutions, we're asked for the number of real solutions for this. And if you have a look at each term, it's all given in terms of tan theta. Not tan 2 theta or tan 3 theta or anything, but just tan theta. So if we can remember the period of a graph of y equals tan theta, this will be a very nice shortcut. So what is the period of a graph of y equals tan theta? Well, we should hopefully recall that the period of tan theta is pi. Therefore, solutions will occur every multiple of pi after the one before. So if we've got the first principal solution as 1.107, the next solution along would be 1.107 plus pi, then 1 plus 107 plus 2 pi, 1.107 plus 3 pi, and so on and so on. So if we just continue up in steps of pi until we get solutions in between 7 pi and 10 pi, what we'd get would be 3 solutions. The first in the range which we need would be 7 pi plus 1.107. This is 7 solutions along, 7 pi multiple. The next one would be 8 pi plus a principal value, and the final one would be 9 pi. So we've clearly got 1 solution here, 2, and then finally 3. So the final conclusion is to say clearly that therefore there would be 3 real solutions to this trig equation. Now let's have a look and talk about differentiating exponentials and logarithms. So, how do we do this? Differentiating exponentials and logs. Well, let's recap first of all that we saw in year 12 that the function y equals e to the x is particularly special because it's its own derivative. So in other words, in particular, when we differentiate e to the x, if y is e to the x, dy by dx is its own derivative. So that's in dy by dx notation, and this over here is in function notation, f of x notation. Now, if you differentiate e to the kx, we'll prove this later, then it's a similar idea, but the constant in the power drops down to the front, and the power stays glued as e to the kx. So it's almost exactly the same, but just the constant comes to the front. So in dy by dx notation, we have it here, or in fx and f prime notation, same deal over here. So like I've said, we'll soon be able to prove the above using results we shall learn about later in this chapter. In particular, what I'm talking about there is the chain rule. Now we need to prove a crucial result, so differentiating a to the x. The first thing we need to do is prove that if y equals a to the x, dy by dx equals a to the x ln a. And we've got free permission to use these standard results above. So if y equals a to the x, then what we can do first of all is just simply rewrite this in this different format. So I'm going to write the same thing first of all, and then just, as I say, write in different format. So if y equals a to the x, then what we can say is that y, we can exponentiate the a to the x. We can say it's equal to e to the power ln a to the x, because e and the natural log are inverses of one another, and so this is the same as a to the x. However, if we do the natural log of a to the x, remembering the laws of logs, we can bring the power to the front, and so in other words, we have y equals e to the power x times ln a. So what we can do now, we can use in the green this result here. So we've got here our constant term, the k, is just ln a. So ln a, because a is a constant, the natural log of a is also a constant. So we can use this result here, subbing ln a in place of k. So therefore, we just simply have dy by dx. Like here, the k drops to the front, so we have ln a times, and then this power stays as it is. So then we have e to the x ln a. But we can put this back into the form e to the power ln of a to the x. So we have ln a times by e to the power of ln a to the x. And like we saw before, e to the power ln of a to the x is the same as a to the x. And so this here, as a final step, we can just replace with a to the power x. So that just becomes a to the power x ln a. Because this here, like I said, is the same as a to the x. And so that result's been proven. We can now adapt this slightly to do part 2. So for part 2, if y equals a to the kx, dy by dx is a to the kx k ln a this time. So this is a slightly different result, but one we can prove in largely exactly the same way. And so what we're going to do here is we're going to use this idea in the same way. So we're going to let y equal a to the kx, then we're going to exponentiate this. So we have y equals e to the power ln a to the kx. So now we can bring the kx to the front of the natural log and say y equals e kx ln a. So let's just think about in this expression for y, in this power, what are the constant terms? Well, the constant term is just any value that is stuck, that isn't going to vary. And so our constant terms here are obviously the k, and also ln a will be a constant. And so using this result here, if we differentiate, then the constant, which is k multiplied by ln a, will move to the front. So therefore, dy by dx is going to be k ln a brought to the front, multiplied by all this thing here, so EKX ln A. So I'll leave K ln A exactly as it is, and then I'm going to repiece this exponential in terms of ln A to the power kx. So just as we can move the power to the front of a natural log, we can bring it back as a power of A. So then we can say it's e to the power ln of A to the kx. But e and the natural log undo one another because these are inverses. So actually, essentially, the e and ln will cancel. So we're just going to end up with a to the kx, which gives us our result. So putting a to the kx at the front, we have a to the kx multiplied by k ln A, which is exactly the result we wanted to prove. And we're going to use this result in some worked examples. So that does need to be remembered. That's not going to be given to you. You need to know both of these results. So let's apply them now with some worked examples. Before we do that though, we also have to remember a few more important facts. So just as we've seen there, dy by dx, if y is a to the x, dy by dx is a to the x ln A. And just as you saw there, if fx is a to the kx, f prime of x will be a kx multiplied by k ln of A. So, differentiating the natural log and the natural log of kx. There's also another two important results we must know when differentiating functions of x in terms of the natural logarithm. So in particular, when we differentiate the natural log, if y is ln of x, then dy by dx is 1 over x. Or in other notation, in function notation, if fx is ln kx, f dash x is 1 over x. So whether it be ln of x or ln of kx, they both differentiate to 1 over x, which I'm going to explain now. We'll also prove why this is the case later on in this chapter. So if you're slightly unsure why this is the case, just bear with me. I will explain and try and convince you, but if this result does hold. But anyway, why is the derivative of ln kx the same as the derivative of ln x when they look completely different? Well, if y is ln of kx, it differentiates to 1 over x. And why is that? Well, we can use the law of logs here. ln of kx, this is the natural log of a product of k and x. If we're taking the log of a product, we can split the product into its individual components. So y equals ln of kx is the same as y equaling ln k plus ln of x. Then if we differentiate both sides, y becomes dy by dx. K was just a constant, so ln k will vanish. Then we just have the ln x to differentiate, which I've told you will give you 1 over x. And so that's where the result comes from. Essentially, it's because we can isolate out the ln of k, which is just a constant, so that disappears anyway. But we'll prove that later on this chapter using something which I'm going to call the chain rule. Well, I don't call it that. It was called that long before I was even alive. So let's have a look at some worked examples as promised. So question 1. Find the derivative function given that y is e to the 3x minus 3 to the power 5x. This looks fairly standard. This one looks awkward. So just to remind you of the results we had previously, we'll need to use this one to differentiate this last term here. So we'll do that one in a bit more depth. So dy by dx, differentiating term by term. The first one is very easy. Remember, e to the kx differentiates to ke kx. So this 3 drops down to the front, so we have 3e to the 3x of that one. Stick in the minus sign, then let's just see what happens here. So in our case, a is 3, and the k is 5. So this is going to differentiate using this result to 3, because our a is 3, to the power of 5x multiplied by k, which is 5, natural log of a, which is 3. So this becomes minus 3 to the 5x multiplied by k, which is 5 ln 3. So just nicking this up ever so slightly, we have 3e to the 3x minus 3 to the 5x times 5 ln 3. We don't really need those brackets, so I'll just remove them for the last step. So that's the derivative function. Question 2. Find dy by dx given that y equals ln x to the 4 plus ln 842x. I'm just going to rewrite y in a slightly different form. Using the laws of logs, ln of x to the 4, that's the same as 4 times ln x. And this one here, ln of 842x, I could use a standard result, but what I'm going to do here is I'm going to rewrite this using the laws of logs from year 12 as ln 842 plus ln x. So now if we differentiate each term individually, 4 is a constant, ln of x will differentiate to 1 over x, so we have 4 times 1 over x. ln of 842, that's just a constant, so that's going to give us nothing. And ln of x differentiates to 1 over x. So if we add together and simplify, we've got 4 lots of 1 over x plus an extra lot of 1 over x, therefore dy by dx is 5 over x. Finally, worked example 3. Find dy by dx given that y equals 2 minus 4e to the 2x all over 3e to the power 5x. This can't be solved yet unless we just rearrange and simplify. So what I'm going to do here, I'm going to divide through by this denominator. So y equals, well, 2 divided by 3 is 2/3. And if I'm dividing by e to the 5x, that's the same as e to the minus 5x. Then minus 4 over 3, so minus 4/3. Then e to the 2x divided by e to the 5x, using GCSE laws of indices. If we're dividing using powers, we subtract the powers if the bases are the same, which they are, both at base e. So the new power of e is these 2x's minus 5x, which is minus 3x. We can now differentiate term by term. So therefore dy by dx equals 2/3 times by this differentiated. So the minus 5 drops down to the front, the power stays as is. And so this differentiates to that. And we have minus 4/3 times by the derivative of e to the minus 3x. Again, the power drops to the front, well, the constant bit in the power does. So minus 3 comes to the front, and then the power stays as is. And so e to the minus 3x differentiates to minus 3 e to the minus 3x. So then simplifying finally, 2/3 times minus 5, that's minus 10/3. So we have minus 10/3 of e to the minus 5x. Then minus 4/3 multiplied by minus 3 ends up with a positive. 4/3 times 3 overall is just simply 4. So we have plus 4 e to the minus 3x. Now it's your turn to try some of these. So, in your blue Year 13 algebra box, if you turn to exercise 9b on page 236, I'm suggesting you try questions 1 to 6, and then the last 3 questions 10, 11 and 12 to get yourself some much needed practice on these core skills, which you'll need for the rest of this chapter and of course your final exams. I hope you found the video useful, as ever. Thank you, as ever, again for listening, and I hope to see you all very soon, or at least hear from you soon. If you struggle with any of the questions, find me in class, or on the channel, or an email. Please do seek help if you need, and keep working as well as you can. Take care from now, and, like I say, see you very soon.